So this is section 5.3, which is graphs of rational functions. It kind of continues off of 5.2, where we talked about the properties of rational functions. So these are our general strategies here for graphing a rational function. The first step is factor out p of x and q of x, the top and the bottom of the fraction, as much as possible. Cancel out any common factors. When you do this, it creates holes in the graph. You find vertical asymptotes by setting q of x equal to 0. Find horizontal asymptotes by using either of the two methods we learned in 5.2. Find x-intercepts by solving p of x equals 0, so taking the top and setting it equal to 0. Find y-intercept by evaluating f of 0, plug 0 in for all the x's. Once you've done steps 1 through 5, plot everything you found. Plot all your asymptotes, plot all your x and y intercepts, do all that stuff. And what you're going to do for step 7 is you're going to pick values of x between each x-intercept and each vertical asymptote and beyond each vertical asymptote to see whether the graph is approaching infinity or negative infinity as the graph approaches the vertical asymptotes. Basically, whether or not it's positive or negative. And then once you've done that, you can connect all points with smooth curves, making sure you follow the behavior you found in step 7. So let's look at some examples of this. I'm going to draw my axis lines in here first. So we have our rational function f of x equals 2x minus 1 over x minus 1. The first step is to try and factor it, but nothing factors on top or bottom, so we really can't do anything there. Next thing is we find our vertical asymptotes by taking the bottom and setting it equal to 0. Moving the 1 over, we have a vertical asymptote at x equals 1. Next, we find horizontal asymptotes using either method that we've learned. I'm going to divide by the highest power of x, which in this case is x. So I'll have 2x over x minus 1 over x over x over x minus 1 over x. Simplifying that, I have 2 minus 1 over x over 1 minus 1 over x. Remember that these fractions that still have x in the bottom, they go to 0. So what I end up with is 2 minus 0 over 1 minus 0, which is 2 over 1, which is 2. So my horizontal asymptote is at y equals 2. And then I'll find x-intercepts. To find x-intercepts, I take the top and set it equal to 0. So 2x minus 1 equals 0. Add the 1 across, we have 2x equals 1. Divide by 2, we get x equals 1/2. So my x-intercept is at 1/2, 0. And then for y-intercept, we find f of 0, which means we plug in 0 for all the x's. So 2 times 0 minus 1 over 0 minus 1. 2 times 0 is 0. 0 minus 1 is negative 1. 0 minus 1 is negative 1. Negative 1 divided by negative 1 is positive 1. So my y-intercept is at 0, positive 1. Now that I found all of this stuff, I want to plot all of it. Let's start with asymptotes. I have a vertical asymptote at x equals 1. So I'm going to go to where x is 1, and I am going to draw a vertical dotted line. And now I'm not drawing it exactly on the line just because it makes it harder to see that way. I'm kind of drawing it next to x equals 1 just so you can see it a little better. Alright, same kind of thing with horizontal asymptote. I have a horizontal asymptote at y equals 2, so I'm going to go to where y is 2, and I'm going to draw a horizontal dotted line. So there's my asymptotes. Then I'm going to do my intercepts. I have x-intercept at 1/2, 0, which is right there. And I have a y-intercept at 0, 1. So these are what I have so far. The last thing to do is to determine my behavior around my x-intercepts and around my asymptotes, my vertical asymptotes. So what I do is I usually make myself a little number line, and on this little number line I write any x-intercepts and any vertical asymptotes. So if I look, I have one x-intercept at 1/2, and I have one vertical asymptote at 1. So that means I actually have 3 intervals I care about for this graph. I care about what happens between negative infinity and 1/2, what happens between 1/2 and 1, and then what happens between 1 and infinity. So what you do is you pick a value in each of these intervals to check to see whether or not you get a positive or a negative. For this first interval, negative infinity to 1/2, I can pick any number, but I'm going to pick x equals 0. The reason why I'm picking x equals 0 is I already know that I get positive 1 when I plug in 0. So I already know it's a positive. I don't have to do any extra work. Alright. Next, I need to pick a value of x between 1/2 and 1. So maybe like, I don't know, 3/4. Okay. I'll take that and plug it into your equation. It doesn't matter exactly what you get. It really just matters if it comes out positive or negative. I'll point up my calculator here so that we can plug in. So I'm going to have 2 times 3/4 minus 1 divided by, parentheses, 3/4 minus 1. And so it comes out as negative 2. Again, I really just care that it came out negative. Alright, and then lastly, I need a number between 1 and infinity. I can pick any number, but I'm just going to do something simple like 2. So take 2, plug it into this equation. So you've got 2 times 2 minus 1 over 2 minus 1. And that comes out as positive 3. So we know that one's a positive. Okay. So now, what we're going to do is we're going to draw in our graph. So when this tells us it's positive, it's saying anytime we're before 1/2, the graph has to be above the x-axis. So it's going to have to go from this point to this point, and it's going to have to stay above the x-axis, and then it's going to flatten out as it approaches that horizontal asymptote. The next little bit from 1/2 to 1 is negative. So that tells us we're going to be below the x-axis there. So in between this x-intercept and this asymptote, we're going to be below the x-axis, and we're going to flatten out as we approach that asymptote. And then the last little bit's positive, which tells us we always have to be above the x-axis. If you remember, that point when we plugged in 2 was at 3. So there's this point here at 2, 3. So our graph is going to go up here in the positives, and it's always going to stay positive. It's never going to go down in here to the negatives. It's just always going to be up here in the positives. And so there is our sketch of that graph. So again, the basic steps are factor the equation, find your asymptotes, find your intercepts, plot them, and then do your little number line sign analysis to figure out where to draw the graph. Okay? Let's move on to our next example. So, we're graphing f of x equals 3x squared over x squared minus 4. And it says note the y values on the graph go from negative 3 to 7. So this is negative 3, negative 2, negative 1. So it means this is 0 right here. I'll draw my y-axis down there. Alright. So the first thing to do is factor the equation. The top does not factor, but the bottom does. It factors into x plus 2 times x minus 2. There's nothing to cancel out, so I really can't do anything there. The next thing is to find vertical asymptotes. We do that by taking our denominator, x plus 2, x minus 2, and setting it equal to 0. That's the same thing as actually setting both of those factors equal to 0. And so we get x equals negative 2 and x equals positive 2 as our vertical asymptotes. Alright, for horizontal asymptote, I'm going to divide by the highest power of x, which in this case is x squared. So I'm going to have 3x squared divided by x squared over x squared divided by x squared minus 4 divided by x squared. So it becomes 3 over 1 minus 4x squared. This 4 over x squared here, because it still has an x on the bottom, goes to 0. So we're going to have 3 over 1 minus 0, which is 3 over 1, which is just 3. So y equals 3 is going to be my horizontal asymptote. For x-intercepts, we take the top of the fraction and set that equal to 0. Divide the 3 across, we have x squared equals 0. Take a square root, we get x equals 0. So our x-intercept is at 0, 0. For y-intercept, we find f of 0 by plugging 0 in for all the x's. So 3 times 0 squared over 0 squared minus 4. 0 squared is 0 times 3 is 0. On the bottom, 0 squared is 0 minus 4 is negative 4. 0 divided by negative 4 is 0. So my y-intercept is also 0, 0. Alright, now that we have all that information, let's plot it. We have a vertical asymptote at x equals negative 2, which is right over here. We also have a vertical asymptote at x equals 2, which is right over here. We have a horizontal asymptote at y equals 3. And then the x and y-intercept are both at 0, 0 at the origin. So there's our graph so far. Now we're going to do our little bit of sign analysis. Okay. Remember, for sign analysis, you're looking at what happens around the vertical asymptotes and around the x-intercepts. So I have a vertical asymptote at negative 2. I have an x-intercept at 0. And I have another vertical asymptote at 2. So I actually have 4 separate intervals: negative infinity to negative 2, negative 2 to 0, 0 to 2, and 2 to infinity. So let's start with this one. I want to pick x equals negative 3. I'm going to take negative 3 and plug it into that equation. So 3 times negative 3 squared. And I'm going to divide that by negative 3 squared minus 4. So it comes out as a positive. It comes out as 5.4. Oops. So it's a positive. I'm even going to note down that the y was 5.4. Alright. In between negative 2 and 0, we can do something like negative 1. So we have 3 times negative 1 squared divided by parentheses negative 1 squared minus 4. And that gives us a negative 1. So it's a negative, and I'm even going to write down y equals negative 1. Alright, at x equal, between 0 and 2, we want to do x equals 1. So we're going to have 3 times 1 squared divided by 1 squared minus 4. And that comes out as negative 1 as well. And then between 2 and infinity, I'm going to do x equals 3. So I'm going to have 3 times 3 squared divided by 3 squared minus 4. And that gives me a positive 5.4, which is kind of nice. Alright. So that kind of tells us our behavior. At negative 3, we're going to be up here at 5.4, which is up here. And it says we're positive all the way until -2, all the way until we get to this asymptote. This graph is going to be positive up this way, and then it's going to flatten out as it approaches that asymptote. Okay. Then it tells us it's negative between -2 and 0. So in between the asymptote and the x-intercept, it's going to go down here into the negatives and keep going down. And then it says between 0 and 2, it's also negative. So going this way, it's also going to go down. And if we wanted to, we actually probably could, just to be precise. We can erase these. We actually do have some points here. We have -1, -1, and we also have 1, -1. So we can kind of go through those, make our graph look a little bit more precise. Something like that. And then lastly, after 2, it tells us we're always positive. When the x is 3, we were up at 5.4, so up here somewhere. And so we're just going to kind of go through that point and then flatten out near that asymptote. So that way we stay up here where we'll always be positive. And so there is our sketch of that graph. Okay. Let's look at example number 3. And draw my axis lines in really quick. Alright, so first step is to factor. The top does not factor, the bottom does not factor, so no factoring can work. Next thing is vertical asymptote. So we would take the bottom, x squared plus 1, and we would set it equal to 0. If we move the 1 over, we have x squared equals -1. Is there any real number that we can square and get -1? No. So there's no vertical asymptotes. This is not solvable in the real number system. All right, horizontal asymptote. Well, if we divide by the highest power of x, that's x to the 4th. So x to the 4th divided by x to the 4th over x squared divided by x to the 4th plus 1 divided by x to the 4th. That gives us 1 over x squared plus 1 over x to the 4th. These fractions that have x's still in the bottom go to 0. So this is going to go to 0. This one's going to go to 0. So I'm going to have 1 over 0 plus 0. So that's 1 over 0. That is undefined. Since it's undefined, that tells us we have no horizontal asymptote. Okay. X-intercepts, we take the top and set it equal to 0. So x to the 4th equals 0. Take a 4th root on both sides, and you get x equals 0. So we have a point at 0, 0. Y-intercept, we find f of 0 by plugging 0 in for all the x's. So 0 to the 4th over 0 squared plus 1. 0 to the 4th is 0. 0 squared is 0 plus 1 is 1. 0 over 1 is 0. So we also get 0, 0 as the y-intercept. Okay. So now it's time to plot. We have no vertical asymptote, no horizontal asymptote, and all we have is an x and y intercept at the origin. So right here at the origin we have a point. So now what we want to do is we want to do our little sign analysis. This time there's only one number I can put on there. The only number I can put on there is 0, because there's only one x-intercept and there's nothing else. So that splits this graph into two intervals, negative infinity to 0, and then 0 to infinity. So if I pick a number on this interval, I'm going to do something like -1. So -1 getting raised to the 4th, divided by parentheses, -1 getting squared plus 1, and I get 0.5 or 1/2. So I get a positive y equals 1/2. And then if I take a number between 0 and infinity, I'm going to do x equals 1. So So 1 to the 4th divided by parentheses 1 squared plus 1. I also get 0.5. So it's also a positive. The y is also 1/2. I'll get those points on there. So at -1, it was at 1/2. +1, it was also at 1/2. And by the fact that these come out positive, it's telling us it's never going to go down here into the negatives. So this is going to keep going that way, and this is going to keep going that way. Now, a good way if you have a graphing calculator to check yourself, make sure your graph looks okay, just go into y equals, and actually just try and graph it. So let's see, x to the 4th divided by parentheses x squared plus 1. Close my parentheses. That still looks okay, so I'm going to hit graph. And there's my graph. So, looks pretty good compared to ours. That's alright. Okay, so there's example 3. Alright, next one. Again, the first thing we do is factor. We have x squared minus 1 over x. That top will factor into x plus 1 times x minus 1 because it's the difference of perfect squares. There are no common factors to cancel out though, so nothing going there. So we'll find vertical asymptotes by taking the bottom and setting it equal to 0. And there's nothing really to solve there. That's just x equals 0. Alright, for a horizontal asymptote, we're going to divide by the x with the highest power, so we'll have x squared over x squared minus 1 over x squared over x over x squared. So it ends up being 1 minus 1 over x squared over 1 over x. Those fractions that are left with an x on the denominator go to 0. So we end up with 1 minus 0 over 0, which is 1 over 0, which is undefined. So this is undefined, which tells us there is no horizontal asymptote. Now this one's a little different though. The degree on top is 1 higher than the degree on bottom. And if you remember from 5.2, we said if the degree on top was 1 higher, then we had a slant asymptote. So let's actually find the slant asymptote. To do that, we're going to do some long division. So I'm just going to kind of set that up over here. X squared plus 0x minus 1 divided by x plus 0. What do I need to multiply x by to get x squared? An x. X times x is x squared. X times 0x is 0x. Subtract. Everything cancels, so I just have 0. And then I drop down to minus 1. So I have 0 minus 1, which is negative 1. That's a remainder. Remember that remainders have no effect, so we don't really worry about that. We just worry about our answer. So our slant asymptote is at y equals x. Next thing is x-intercepts. Take your top, set it equal to 0. So x plus 1 times x minus 1 equals 0. Which means x plus 1 equals 0, or x minus 1 equals 0. So we get x equals negative 1 and x equals positive 1. So we have negative 1 comma 0 and we have 1 comma 0. Okay. Y-intercept. For y-intercept you find f of 0. Well, if you plug in 0, you get 0 squared minus 1 over 0, which gives you negative 1 over 0, which is undefined. Since you get an undefined there, that tells you there is no y-intercept. Alright, so now we've found all our stuff. Let's plot it. Vertical asymptote is at x equals 0. So it's going to be right here along the y-axis. I don't have a horizontal asymptote, but I do have a slant. My slant is y equals x. That's a line that has a slope of 1 and a y-intercept of 0. So it's going to go through this point, this point, this point, this point, this point, this point. I'm also going to go backwards a little bit. So that is our slant. We have an x-intercept at -1, 0, another one at +1, 0, and we have no y-intercept. So there's where we're at. So the next thing we want to do is our little bit of sign analysis. This time we're going to have 3 things on there because we have 2 x-intercepts and 1 vertical asymptote. So we're going to have -1, 0, and 1. If I pick a number before -1, like -2, I can take that and plug it into this equation. So I'm going to have -2 getting squared minus 1. I'm going to be dividing that by -2. And that gives me a -1.5. Right. In between -1 and 0, I can do something like -1/2. So -0.5 getting squared minus 1 divided by a -0.5. That gives us a +1.5. Right. And then in between 0 and 1, I can do something like x equals 1/2. So 0.5 squared minus 1 divided by 0.5. I get a -1.5. And then between 1 and infinity, I can do something like x equals 2. So we'll have 2 squared minus 1 divided by 2. And that gives us a +1.5. And then that'll help us get our graph. So when x is -2, we're at -1.5. And that's telling us we're going negative, so we're going to go down here into the negatives, and then we're just going to keep following along that slant asymptote. Here in between these two, at -1/2, it's up at 1.5, which is right there. And it's telling us it's positive, so it's going to kind of go up here into the positives, and then it's going to flatten out as it approaches that asymptote. In between these two, at x equals 1/2, we're down at -1.5. That's telling us it's negative, so we're going to go down this way and flatten out as we approach that asymptote. And then in our last interval at 2, we're at 1.5. So we kind of go like that. And so there is our graph of our function. Okay. Let me redraw that really quick. Alright, so our next one is f of x equals 2x squared minus 5x plus 2 over x squared minus 4. First thing to do is try and factor it. To the top, 2x squared means I need to have 2x times x. A 2 means I need to have 1 times 2. Make it -5 in the middle, they're both going to need to be negative. So that way this 2x gets multiplied by this -2 and becomes -4x. -1 times x makes -1x, and -1 and -4 make -5 in the middle when we add them. On the bottom, x squared minus 4, that's the difference of perfect squares, so it'll factor into x plus 2, x minus 2. Alright, so this is the first time we've seen this. We have a common factor here. We have these x minus 2's that can cancel out. This actually creates what's called a hole in the graph. Now, the location of the hole you find by taking that factor and setting it equal to 0. So if you move that over, you get x equals 2. And then to find the y value, you just take that and plug it into the reduced one, to the simplified equation. So I'm going to go to my calculator and I'm going to do parentheses 2 times 2 minus 1 divided by 2 plus 2. And I get 0.75 or 3/4. Okay. So my graph is going to have a hole in it, and I'll show you in just a second what that will look like graphically. Alright. Next thing is vertical asymptotes. Well, we only have one thing left on the bottom, so we're only going to have one vertical asymptote. At x plus 2 equals 0, which means x equals negative 2. Horizontal asymptote. You can either do it based off the original, or you can base it off of the reduced one. I'm going to use the reduced one. So my highest power of x is x. So I'm going to have 2x divided by x minus 1 divided by x over x divided by x plus 2 divided by x. And so that'll simplify to 2 minus 1 over x over 1 plus 2 over x. These fractions that are left that still have x in the denominator are going to go to 0. So I really have 2 minus 0 over 1 plus 0, which is 2 over 1, or just 2. So y equals 2 is my horizontal asymptote. Next thing is x-intercepts. Look at your factor that's left on the top. Set it equal to 0. So 2x minus 1 equals 0. So it means 2x equals 1, and x equals 1/2. So we have an x-intercept at 1/2, 0. And then lastly, y-intercept, we find f of 0. Again, you can do it in the original or you can do it in the reduced. It doesn't really change anything. I'm just going to do the reduced. So 2 times 0 minus 1 over 0 plus 2. 2 times 0 is 0, minus 1 is negative 1. 0 plus 2 is 2. So we get negative 1/2. So 0, negative 1/2 is our y-intercept. Alright, so now we get to plot all of this stuff. Let's start with the hole. Our hole is at 2, 3/4. So I'm going to go to 2 and 3/4, and what I'm going to do is I am going to draw an open circle. I'm not going to draw a complete point. I'm just going to draw an open circle to represent that hole. And I'm going to do my asymptotes. X equals negative 2 is over here. So there's my vertical asymptote. Okay, horizontal asymptote is y equals 2. Alright. X-intercept at 1/2, 0. Y-intercept at 0, negative 1/2. So there we go. There's what we know so far. The last thing we're going to do is our sign analysis. This time we're going to have 2 points on our little number line because we have one vertical asymptote and one x-intercept. So we're going to have negative 2 and positive 1/2 as the things on our number line. Alright, so we need a number between negative infinity and negative 2. So let's do negative 3. I'm going to use the reduced form for plugging in. So I'm going to have 2 times negative 3 minus 1 divided by, parentheses, negative 3 plus 2. And that gives me a y value of 7. Oops. So it is a positive, the y value equals 7. In between -2 and 1/2, I'm going to use 0, because I already know when I plug in 0, I get a negative. I get this -1/2. And then lastly, between 1/2 and infinity, I can pick any number. I'm going to pick x equals 1. So if I plug in 1, 2 times 1 minus 1, divided by, parentheses, 1 plus 2, I get 0.33333, which is 1/3. I have a positive, and y equals 1/3. Alright, so this first little bit tells me at -3, which is right here, we're up at 7. 1, 2, 3, 4, 5, 6, 7. It'd be up here somewhere. And because it's positive, it says we're just going to stay up here in this little quadrant. So we're going to kind of come down and flatten out. And we'll keep going up that way and flatten out near this asymptote. The next little bit says in between these two, in between -2 and positive 1/2, I have to be negative, so I have to go down through this y-intercept, and then I got to keep going negative as I approach that asymptote. And then lastly, when x was 1, we got y was 1/3. It's right there. And it tells us it's always positive, so it's going to go up, connect to that point, connect to the hole, and then it's going to keep going up, and it's going to flatten out as it approaches that horizontal asymptote. I do want to show you the graph of this one really quick, just so you can kind of see it. So on the top, I have 2x squared minus 5x plus 2 divided by, on the bottom, I have x squared minus 4. So when I hit graph, you see it kind of looks like our picture. But you'll notice that it doesn't show a hole like ours does. Here's what happens. If I hit trace, and I go to where this hole is when x is 2, watch what happens. It says when x is 2, y is, and there's a blank. It's because this graph has a hole in it, and the calculator doesn't know where the y location of the hole is. It just knows there's nothing there. So it says, oh, it's blank. There's a hole there. Alright, so that is example 5. Alright, the last thing we're going to look at is an application for rational functions. So we have what's called a cost function C, which businesses use to figure out how much it costs them to build X number of things. And the way this cost function works is you have C of X equals your fixed costs that you always have to pay, things like electricity, water, whatever. And then you have plus CX. CX is the cost per unit times the number of units. So this C represents how much each unit costs you. X represents how many units you're building. Now, this function by itself is not rational. It's likely to be polynomial. But when we want to find the average cost per unit, basically on average, how much does it cost us to build this, what we have to do is take our cost function and divide it by the number of units, divide it by X. This gives us the average cost, which is C bar of X. And it's just our cost function, fixed cost plus Cx, divided by our number of units, so divided by X. And because there is this division, it is a rational function. So let's look at an example that uses this. So it says, suppose a company that manufactures a robotic exoskeleton has a fixed monthly cost of $1 million and it costs $5,000 to produce each robotic system. Part A asks us to write the cost function C of X for producing X robotic systems. So we say C of X equals, what are our fixed costs? The fixed costs are $1 million. There's that. Plus, what is our cost per unit? It costs us $5,000 per unit. and then we multiply it by how many we have, which is x. And so there is our cost function. Part B asks us to write the average cost function, C bar of x, for producing x robotic systems. Well, to find the average cost, you take your cost function, which is 1 million plus 5,000 x, and then you divide it by how many systems you're building. In this case, we're building x systems, so we divide it by x. All right. Part C asks us to find and interpret C bar of 1,000, C bar of 10,000, and C bar of 100,000. So that means we're just going to be plugging in. So I'm going to start with 1,000. I go to my calculator. So on top I have 1,000,600 plus 5,000 times the number of units. This time we're doing 1,000 units. And then we're going to divide that by how many units, which is 1,000. And so we get 6,000. And so when we interpret it, the idea is when we build 1,000 systems, the average cost is $6,000. Alright, let's look at 10,000. What if we build 10,000 of these systems? So I'm going to have 1 million plus 5,000 times 10,000. And then we're going to divide that by how many, which is 10,000. So we get 5,100. So when we interpret that, we say when we build 10,000 systems, the average cost is 5,100. Alright, and then what happens when we build 100,000 of these robotic systems? Well, we've got 1 million plus 5,000 times 100,000. So let's say that's 1,000, 10,000, 100,000. And we're going to divide that by 100,000. That comes out as 5,010. And so if we're interpreting it, we can say when we build 100,000 systems, the average cost is $5,010. And notice, as the number of systems has gone up, the cost has dropped. And that's usually true with producing things. The more of them that you produce, the cheaper each one is to actually make. Alright. And then we have one last part to this problem. Part D asks us, what is the horizontal asymptote for the graph of the average cost, C bar of x? Describe what this represents for the company. Remember, C bar of x is this function, 1 million plus 5,000 x all over x. We want to find the horizontal asymptote, so I'm going to divide everything by x. So 1 million divided by x plus 5,000x divided by x over x divided by x. That first one won't simplify, so it's still going to be 1 million over x plus the second one, the x's would cancel, so I just have 5,000. On the bottom, the x's would cancel, and I would just have 1. This fraction that still has an x in the denominator, remember, goes to 0. So what I really have is 0 plus 5,000 over 1, which means I have 5,000 over 1, which means I just have 5,000. So y equals 5,000 is our horizontal asymptote. Now, let's describe what this represents for the company. Remember that horizontal asymptotes represent end behavior. So what we're saying is, as x goes to infinity, c bar of x is going to get closer to 5,000. Now, what does that mean for the company, though? This is just a math statement. What does that really mean for the company? Well, x represents robotic systems. So we can say, as they produce more systems, and then this c bar of x is the average cost. So we can say the average cost per system approaches $5,000. So that's kind of what it means for the company. As they produce more and more of these systems, the average cost per system is going to approach $5,000. And you can actually see that if you go into y equals and look at this function. So if I put in 1,456 plus 5,000 x, and then divide it by x. I'm going to change my window a little bit. I'm going to make the x go from 0 out to, let's say, 1,000,000. And I'm going to make the cost go 0 to, say, 8,000. I think that'll be okay. So if you look, when I only make one system, when x is 1, this is how much it costs. It costs 1,005,000. But if I build 100, the cost jumps down to 15,000. If I build 1,000, like we checked earlier, the cost drops to 6,000. What if I had built 1,000,000? When I build 1,000,000, the cost has dropped all the way down to $5,001. Okay? And I can even make it go less, like, as I build more and more as I keep going, as my x gets bigger, this y value keeps going. So, like, what if we built 2,000,000 of these? I need to make my window bigger if I want to build 2,000,000 of these. So let's see, let's make x max go to 2,000,000. So if I go out to 2,000,000, look, it only costs $5,000.50 if we're all the way out making 2,000,000 of these units. Do you see how it's getting closer and closer to 5,000? The cost is going down, so we can kind of see that. Alright, so that is the end for this set of notes. As always, email me if you have any questions, and I'll try to get back to you.